Hello everyone, welcome to the channel. Today we are going to discuss about the cell and tube heat exchanger. As many of you asked me to simulate a cell and tube heat exchanger where the hot fluid is in its vapor form and it is condensate after heating the cold fluid. So before starting the tutorial, I want you to learn or to remember few things. Like here I am not gonna do the design of cell and tube heat exchanger, I am just gonna simulate it. So basically you already know about the area, the number of tubes, the internal and outer diameter of the tubes, and the cell diameter. All of the designs you have already done for your process and you just want to simulate and validate it. So let's start the today's tutorial. So here our objective is to simulate the cell and tube heat exchanger and find the amount of water. I have choose the hot fluid as a water that is required to heat the cold fluid from certain temperature to another temperature, and also find the temperature that will be gained by the cold fluid, so that the hot fluid only condensate from its vapor form to the liquid form. So water is a hot fluid that will enter at 100 degrees centigrade and condense at 1 bar pressure. Benzene heats up from 25 degrees centigrade at a 1 bar pressure of inlet steam, and 3600 kg per hour is the mass flow of the benzene steam. So with this information, let's go to the simulation window and process it. So once you go there, you just need to click on create a new simulation window. Now click on next, then choose water, then again choose benzene by typing the name in the search bar, and after selecting, click on next, then select the SRK model and click on next. Choose system of unit as a C5, click on next, and finish. Now you will see this window. For temporary, turn off the auto simulator so that you can first design your flow sheet. Now just okay. So first I will make inlet stream name as water, which will be steam. So water is steam at 100 degrees centigrade. Initially I will put only 50 kg of steam because steam has a high amount of latent heat, and make the mole fraction of benzene 0. I will accept this. So now you can see the whole steam will leave water and vapor phase mole fraction should be 100 should be 1. Now click on 2, it should be methanol, not methanol, sorry, benzene cold. Name third as water liquid, and name fourth one as benzene hot. Cold inlet, hot fluid, and heat exchanger. Now come to the make it as a cell and tube heat exchanger temperature. I want the hot fluid temperature to be 100 degrees centigrade. Now what you need to do, go to the edit cell and tube heat exchanger properties. Here you see it is asking for cell in series. You gonna use one cell, two cell, or more than this. You can use that. Cell passes, here you can understand when we are talking about one pass, the tube side fluid enter once and goes out, but in two pass it enter once and then again goes back to the same side. So it just increase the time of the cell side fluid in the heat exchanger. Internal diameter 500 mm, you can change based on your calculations. Fouling factor is 0 as I don't consider any fouling now. For baffle spacing you can decide, but here is 250, means like for a 5 meter length, every 250 we have a baffle that are increasing the turbulence in the heat exchanger. Baffle cut is 20%. Basically it will be the baffle length is the 0.8 of the 80% of the 500 mm, it only left 20% clearance for the fluid at cell side to go, which will create a turbulence and increase the heat transfer efficiency of the fluids. Internal diameter of tube is 50, external 60, basically 10 mm thick diameters of tubes are used of a length 5 meter. So this all parameters you can calculate or keep as same as I am going to same, as I am using same because I want to use the standard exchanger that is given by the DWSIM, because I don't do any design for it. I will do a designing of this, how to design a silent tube heat exchanger, and upload the video on the channel. In the design section of this video you can see the link also. I have kept a separate playlist for the tutorial that contains about the designing of these things. Now I choose passes per cell 2 because it will increase the heat transfer efficiency. Tubes per cell 50, tube spacing 70. I layout you can choose triangle, rotating square, rotated square. This I am gonna choose triangle. Now fluids in a tube. So in general what we do in the process, we heat up the process fluids which are sometimes reactive to the metal, so we kept them in a tube so that we only lost the metal when they are reacting with the tubes. Only the fouling of the tubes should happen so that we can clean them using the water. If we kept them on a cell side, what will happen, they will foul the tubes also as well as the cell, because they are coming in the contact of both. So and cleaning will not be very nasty for these cases to clean the tube side from the top, because from here you can see if pass water at a high pressure, then the tubes will automatically clean. So choose the default setting of the silent tube heat exchanger. But now you need to know, remove this, press the solve button. Okay. Let me come here. It says 3600, water 150. Okay, now I will make it as at least 45. Let's say I make it as a 99. Okay, so first what will I do to just calculate something, I will run it as a silent tube heat exchanger rating so that I get some. Okay, it is talking about property package. Okay, so I think we have selected a wrong property package, so I will change it. What I will do, I will go to the thermodynamics from setting, remove this, and now I will use SRK advance. Now I will just say please. Okay. Not an issue. Let's once check all the things how we suppose. Okay, yes. So I need to make water 0. I will accept it. Now you see this is the problem, because I mix benzene and water together and the property package was not able to calculate them. So I use SRK advance because advance have a more correction done to it. Initially I choose the SRK only. So now you can do these kinds of things, but now let's me first add the things like property table so that we can analyze what is going on. So first I will add water, temperature, mass flow, and molar fraction vapor. You can see it is almost a vapor only. I will add water, liquid, temperature, mass flow, molar fraction vapor. Here you can see temperature is 56. I will add benzene, cold, temperature. No, I want to know the hot temperature, no? How much benzene is gonna hot. So I will add benzene hot, temperature, mass flow. That's it. Okay. So now go to the water. Make water as 100 degree. I am gonna use water at 100 degree centigrade. So you see temperature of water is 100 kg per hour of water. So temperature of water is now 96, and molar fraction of vapor is 0 because water is condensed, and also the liquid also lost some of its heats. Now I will do 1110, and now you see water is at almost 100 degrees centigrade and little bit of vapor is left. Now I will make it as 112. You can see as I am increasing the water flow rate, only the condensation is happening and amount of vapor is reducing. I will make it as 118. Now you see amount of vapor is again increasing. Now I will make 120. Okay, let me make it 120. So from here you just observe how the amount of vapor is. So you see now amount of vapor is start increasing, and at 113 you see the amount of vapor is very much less in the mole fraction of water liquid. So what I will do, I will make it as a 115. Now you see vapor is very much come close to yes. So this is the almost state that you can, I will say, so 116 is the most optimized flow rate of water. So at 116 kg per hour of flow rate of water, I am just using the condensation of the steam to heat the benzene from the temperature of 25 degree to temperature of 67 degree centigrade. Now you might encounter the design problems where this temperature you also need to negotiate. So in that scenario, what you need to do, you go here, you might need to, here I am doing selective heat exchanger rating, you go to selective fouling calculations, and in that you just change it to, let's say, 80. Now you see water has some amount of vapor because it is condensed, as well as at any point of movement water when it is close to 99 it had some amount of vapor in it when it condensed and lose some amount of heat. So you can use the fouling calculations to figure out the final temperature and vapor mole fraction of water when you know the final amount of temperature in the benzene. So as per our objective, we know how to simulate a selective heat exchanger. Now for the flow rate of water and the temperature of outer fluid, that will be achieved when water is gonna be taken only the what I will say, taken only the condense, only water is get condensed from steam to the liquid phase, then the 67 degrees centigrade is the temperature that can be achieved. So from this you can come up with two informations, like 67 degrees centigrade of water temperature can be achieved when 116 kg of water is required, steam is required just to condensate and heat up it to the 67 degrees centigrade of temperature, the benzene flow rate of 3600 kg per hour. And what else you can do, sometimes what happens, as I am what I will let you know, you can play with the property of the heat exchanger also. I am using a long heat exchanger of 5 meter. If you reduce the heat transfer time, then only the condensation will able to happen, and the temperature that is attained by the cool fluid will also be limited. So in that scenario you might make it as the length of the tube set 4, which will decide the length of the heat exchanger. So in this scenario you can play with the various properties of the selective heat exchanger. So this is the end of the video. Thanks for watching.